Now we're going to see some problems on vectors. This is part of the requirements. In web courses you have an entire page devoted on how to find and what resources you can use to catch up. So this is part of the things that you should know before Physics 2053. But anyway, I just want to highlight the things that you actually need to know, so it's easy to remember. The first things that we need to know for vectors is going to be how do we add vectors. Note on notation. Sometimes in books, on slides for instance, I use bold to note that this is a vector. Remember, vectors is just a generalization of a number that has both magnitude and direction. And sometimes in physics we prefer to think of it as an arrow. So it's an arrow that's pointing in a certain direction. The arrowhead is giving us the direction. The length of the arrow is telling us what's the strength. And that strength, if for instance the vector is velocity, for instance, we call speed, right? Which is just the magnitude. Other times you're going to find that in books they just put the small arrow ahead of the, or on top of the letter that we use to describe the vector. Both are notations. As any notation is arbitrary, so the one that you use, be consistent not to confuse yourself, and be aware that it's not the same to use a scalar than using a vector. So the operations that you need to know is how to add vectors, how to subtract vectors, how to, let's just write C. How to multiply vectors times a scalar, so let's write n being a number, or a scalar, we also can say a scalar, right, which is just to say it's just a number, so like 1, 3, 2 millions, 3.7 pi, and then a vector, right? And you need to know as well dot product or a scalar product. It is the same thing, which is just multiplying one vector times another, which it's given by the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle in between. These are all the things that you need to know about vectors. Of course, as well, you need to remember that vectors are expressed numerically in a given coordinate reference. So if this is A, then I can actually describe then my A vector according to the length of that vector into my x and y components. And so I can just always say that the vector is just given by the x component and the y component. And so we bear in mind this idea that vectors are just simply a generalization of a number that uses, let's say, two numbers to express the same amount. We also can find that the modulus of the vector is just x component squared times y component squared. And again, so let's do this not to confuse people. Let's do this. So then we can just find that this is a sub x and this is a sub y, right? So then I have this, and then I also find an angle, and of course the angle according to SOHCAHTOA, so we can know that, for instance, if we use the sine, that's going to be opposite by divided by, sine is so it's sine of theta is going to be to opposite divided by hypotenuse. The hypotenuse actually is the magnitude of the vector, right? And so it would be a sub y divided by modulus of a. If this was the cosine, it would be SOHCAH, so it's going to be adjacent, so a sub x divided by hypotenuse. And finally, TOA, so we have that the tangent of theta, we can just write tangent. The tangent of theta, which is that angle, is going to be TOA, so it's going to be opposite divided by contiguous, which is a sub y divided by a sub x. And so if I want to find the angle and I know the components of the vector, I can figure out the direction. This angle we call direction, this we call modulus. In here we describe the vector in components. So this is all that needs to be known. We can just say that this is obviously going to be ex plus bx ay plus by. When we are adding vectors, we just add their components one to one. When we're subtracting vectors, we're doing the same thing, subtracting the components. When we are multiplying times a number, we're just simply doing multiplying the number for every one of these components. And just realize this is sometimes called scaling, and that's why it's actually called a scalar, because it's equivalent to say if I have a vector and I call this a vector, then 3a is just taking this vector and doing 1, 2, 3 times. So this is 3a. So what have I done? I have scaled up the vector. So I call this a scalar because it just helps me scale up the vector. So that's the ideas that you need to know about vectors. So let's realize something about the dot product or the scalar product. Again, it's given by the modulus of the first one times the second one. If you want to do it in components, of course, this is ax times bx plus ay times by. So you multiply components and then add them together. That's going to be the same thing. There's two ways. But I want to focus on this just to realize something about the dot product, what exactly is happening. Let's paint our axis of coordinates, and here we have y, and here we have x, and then let's decide that this is vector a, right? And then let's paint vector v here. That's going to represent vector b. And I'm asking what's a times b graphically, right? So if I take this, I have a times b cosine of theta, where theta is this angle. Let's focus on the triangle that is formed by the vector b and the axis of coordinates and the angle theta. So now I can realize that I have a right triangle where the hypotenuse is going to be given by the magnitude of vector b. And how much is this? How much is that? Well, that's actually the projection of b onto the x-axis. So that's actually the component v sub x. And so I can realize that if I do here SOHCAHTOA for the cosine, the cosine of theta is going to be actually equal to SOHCAHTOA. So it's going to be the adjacent, which is b sub x, divided by the hypotenuse, which is going to be the modulus of b. So I can take b, multiply in here, and I have bx, right? So I found that this is bx. Let's go back here. We have found that this is bx. And a, in this particular example, we align a with the x-axis, but it could have been aligned anywhere. At the end of the day, what this means is that we are projecting vector b onto the direction of vector a. So the dot product it's doing is multiplying the strength or the magnitude of the vector a times the strength or the magnitude of vector b into or onto the direction of vector a. That's going to be relevant because when we use forces, and for instance we ask how much is work done, and work is force times displacement, we're going to have a dot product. And there's only work whenever there is certain component of the force in the direction of the displacement. If they are perpendicular, you'll see it's 0. So this is coming from here. If there is no projection of the force into the direction of motion, then there is no work done. We'll see that on chapter 2, but these are all the things that we need to know for vectors.